Good morning. Welcome back one more time to Physics 4B Lab. And in class now we're looking at circuits. We've put a bunch of resistors into these different circuits and we've analyzed what the voltages and the currents are. So in lab, that's what we want to follow up with. We want to look at resistance and current. Specifically, what our objective is for the day is to be able to measure the resistance for some different objects. So I've got those right here on this front table. This is just a bunch of wire. So it's a coil of wire, so it's really long. I think it's more than 1 kilometer or something. That seems kind of remarkable, but it's a really, really long piece of wire, and it's been wrapped over and over and over and over and over. And so we want to find out, how much resistance is in a really long piece of wire. And it turns out not much. It's only like 1 or 2 ohms of resistance, and that's kind of what you would expect. I mean, we run wires all over the place, right? We can run wires for long, long distances, and we expect those wires not to have much of an effect on our circuits. So it doesn't have that much resistance, but we'll be able to go in and measure it. Now, for this coil of wire, we've got 3 different circuits set up where we want to be able to go in and measure the resistance. So circuit A, circuit B, and then something we're going to call a bridge circuit. And in fact, that's going to give us a chance to go in and talk a little bit about measuring devices. When we take a look at using these circuits, using circuits A and circuit B to do a measurement, one way we could measure a resistance is say, look, if I can measure a voltage and I can measure a current, if I can measure the current going through this device and I can measure the voltage across it, that should give me enough information. That's enough. I should be able to go in and calculate a resistance from that. So that would just be R is equal to V over I. Now to get the current, what I've done in the circuit, I got a battery here, what I've done is I've put an ammeter in series with this resistor, with this wire coil. Now by putting an ammeter in series, that's a direct measurement. Whatever current is going through the resistor, it's got to go through the ammeter. That seems pretty reliable. So I should be able to get a good, reliable value by getting I need a precision ammeter to do this. But if the ammeter is reliable, the current measurement should be equally reliable. Now the problem here is getting a current and a voltage reading both at the same time. And there's a couple of problems here. First of all, what I might want to do is I might want to attach my voltmeter here. By attaching the voltmeter here, the ammeter will continue to give me a good reading. Now, the problem here is that the voltmeter is, instead of just measuring the voltage across the resistor, it's also measuring the voltage across the ammeter. And the ammeter has its own resistance to it. So it's like measuring the voltage over 2 resistors in series. So the problem then is that the voltmeter is going to read too high. Instead of just getting the voltage across here, across the resistor, it's also going to read the resistance across the ammeter. Now there's a way around that. What we can do is we can move on to circuit B. In circuit B, what we've done is we've reattached the voltmeter. So this voltmeter is now directly attached to the terminals on the resistor. So if I get the voltmeter so that it's attached very close to these 2 contact points on this wire, that should give me a good, reliable measurement of the voltage. So the voltage now is looking pretty good. The problem now is, since I've moved the ammeter out of that region, the ammeter now is not directly in series with the resistor. The ammeter is off on a different branch of the circuit, and by looking at this, I can see that some of the current is going to go through the resistor, but some of the current is going to go parallel through the voltmeter. So these ammeters and voltmeters are, the ammeters and voltmeters themselves have a certain amount of resistance to them, and there's a magnetic effect where they move a needle back and forth. We'll see what our ammeters, actually they're right here. So here's an ammeter and a voltmeter, and it has a needle here that moves back and forth depending on how much current is passing through. Now, the voltmeter actually works the same way. What it does is it measures actually how much current is passing through it. So that becomes a problem. Now, here's kind of the idea behind building an ammeter and a voltmeter. If I'm building an ammeter, I want it to have very, very, very really low, very, very low resistance. The idea is for an ammeter, I don't want the ammeter adding to the resistance in this circuit. So in order to make the effect of an ammeter small, I give it a little bit of resistance. Ammeters have to be built right into the circuit, right? So I got to be able to measure whatever current's going through that resistor. I got to be able to measure what that is without disrupting the circuit. If the ammeter has a lot of voltage, well, that's going to change the way that the circuit behaves. So ammeters have very, very low resistance. Now, voltmeters are different. Voltmeters are actually designed in a way where I want a lot of resistance in the voltmeter. And that's to make sure that very little current in the circuit goes through the voltmeter. I don't want current going through the voltmeter. I want the voltmeter is going to be placed in parallel. And in fact, I've kind of emphasized that point by putting these little arrows in there. Those arrows still represent a contact, but I guess what I'm trying to emphasize here is the ammeter is part of the main circuit. The voltmeter is not. The voltmeter is kind of off to the side by itself. So for the ammeter, very low resistance is the way we want to build them. For a voltmeter, very, very high resistance is the way we want to build them. Now, something to keep in mind here is that means that when I've got a meter out, when I have a voltmeter out, voltmeters are pretty rugged, which means whatever I connect to it, it's got a lot of resistance. It's going to be unlikely that I ever burn out a voltmeter. Voltmeters just have so much resistance to them. But ammeters are actually, there it is. Ammeters are actually pretty fragile because they have very little resistance, and if by accident I connect an ammeter in the wrong way, I could burn it out. So ammeters are inherently more fragile than the voltmeters because they have such low resistance. So that's what circuit A and circuit B are. And given what we've talked about, we're guessing that since the voltage here is going to be read too high, when I carry out a calculation for the resistance, I'm going to end up with too high of a value using circuit A. If I go to circuit B, it's the current that's going to get measured as being, the meter is going to read higher than what the current actually is. And that says this also will give me a false reading, but it would give me a reading that's too low. So one way we could approach this is we could do both. We could do circuit A and circuit B. We're guessing that circuit A is going to come in, the resistance calculation will come out too high. And then for circuit B, the resistance calculation will come out too low. And we'll take something in between and hope that there's not too wide of a range there. All right, so that's what circuit A and B are going to look like. Now, we're going to move on to this other circuit. What we've seen so far is there is this concern going on that maybe meters are always going to get in each other's way. The voltmeters and the ammeters are going to get in the way of each other. Is there a way we could do a simultaneous measurement that would be reliable? And it turns out there is. It turns out that if we design a different sort of a circuit, this bridge circuit, we can actually make a reading where the meter, the measuring device, doesn't disrupt the measurements. And here's how it works. In a bridge circuit, let's say that we're trying to measure the resistance of some object. I'm going to call that R sub x. Now that's the object we want to measure. Now in series with that, what I'm going to place is R1. Now in our circuit, R1 is going to be this precision resistor. So this is what's called a precision resistor box. And what it allows us to do is just dial in a resistance, which is kind of interesting. That's kind of fun. It says that we can, this will go from, I guess these are the 10,000s, these are the thousands, these are the hundreds, and these are the 10 ohms. Oh, 1 ohms, I'm sorry. So this goes as high as 9,000 or 10,000. Yeah, it does go to 10. It goes as high as 10,000 ohms. This goes as high as 1000 ohms. This goes as high as 10 tens of ohms. And this goes as high as 10 ones of ohms. So I can set anything between, 11,110 ohms on this just by placing them all in series. Okay. Now, we're going to depend on this being precision. It claims that everything here is accurate to 1%. So this is a 1% reliable device. That's going to become important. So here's what I'm trying to measure. Let's say that we're measuring this wire coil again. So I'm going to get the wire coil here, and then I'm going to put that in series with my precision resistor box. Now what we can do is we can add to that what we can do is we can put in a couple of other resistors, R2 and R3. Now what those look like for today's lab is it looks like this. Okay, this is our resistor. It runs from here to here, and it is a 1 meter piece of wire, uniform wire. And so what happens is that R2 and R3 get divided up. What we do is we take this 1 meter wire and divide it into 2 sections, and wherever we decide to divide, let's say I divide it right in half. Well, if I divide this in half, I'm going to have half the resistance on one side and half the resistance on the other. Okay. And so what we can do is move this from location to location. Depending on how it gets divided up, the ratio of those lengths, L2 and L3, those are going to be in proportion to the resistances. So what we do is we connect everything up, and then we adjust the lengths until this galvanometer reads 0. Now, if you remember from last week's lab, a galvanometer is something, it's just measuring current. And if the galvanometer is reading 0, so I want to get that galvanometer to read 0, because when it's reading right at 0, that tells me that the ratio of voltages on this side in fact, the voltages on this side match the voltages on this side. The voltage is being divided up with the same ratio. Now, if Vx over V1, that ratio, matches V2 over V3, well, this ratio is going to be the same as L2 over L3. So that means that I can measure the length of this precision resistor wire, and that is going to tell me what the ratio of these voltages is equal to. Now, ratios of voltages are proportional to ratios of resistances. If I've got no current going through the galvanometer, then I can treat these two resistors as having the very same current going through each one. If none of the current is going sideways here, right, the galvanometer is reading 0, that means that the currents on both sides match, and that says that the resistances, the ratio of resistances, will match the ratio of lengths. So that gives me a way to make a measurement while the measuring devices are reading 0. If the galvanometer is reading 0, it's not disrupting the circuit, not having any effect on the circuit at all. And so this is a way where we can get measurements without disrupting the circuit from the meter. Now, we want to be able to have a galvanometer that reliably lets us know when we're at 0, and we've got that. That's pretty easy to make. We do need a precision resistor box. And the resistor boxes we have, actually we just got these recently. This is kind of the first time that I've used them. These resistor boxes are advertised to be accurate to 1%. So we could get 1% accurate measurements on all of our readings. And that would be really good. All right, so everything looks good with that. What we're going to be able to do is work with some data tables that look something like this. Now, in addition, when we move on to the bridge circuit, we want to bring in the wire coil and see if circuit A, we'll find out what circuit A tells us the resistance is, find out what circuit B says, and then find out the bridge, and we can compare all of those. With the bridge circuit, what we can also do is we can bring back in these voltmeters and ammeters and find out how much resistance they have in them. Remember we talked about, this is just a resistor with some other, with a magnetic loop of wires moving our needle. Same thing here. So we could actually measure how much resistance there is in these two devices. The ammeter we're guessing is going to come in really low. The voltmeter is going to come in really high. We'll find out if that really works the way that we imagine that it does. So for the bridge circuit, we got 3 different things we want to measure. The wire coil, the voltmeter, and the ammeter. We're going to measure all of them. Okay, so that's what we've set out to do. Now, another objective we have for the day is we want to measure the resistivity of copper. Now remember, resistivity is this inherent property of a material to have resistance. It's what's kind of the inherent resistive properties of the material itself. And we're guessing copper's is pretty low because that's what we use for all of our wiring. And we've seen these in class discussion. So we've seen the resistivity of copper in some examples there. So to calculate the resistivity of copper, what we're going to do is we're going to come back to these wire coils. It turns out this wiring it's copper. So this is made out of copper. Now it's got insulation on it, right? If this were just purely copper wrapped all together, everything would just conduct, it would short circuit. So this is copper wire with a thin layer of some sort of insulating, copper oxide or something that's put around the outside. So what we can do is this. We can come back to our formula for resistance that depends on resistivity, the length of the wire divided by the cross-sectional area. So what we have to think of is taking this coil of wire and unwrapping it. Now I'm not really going to go through and unwrap it, and you guys aren't going to do that either. Like I was saying, I think it's something like 1 kilometer. I'll have to check and see. It's at least in the hundreds of meters of wire that we have here. There's actually 5 layers of wire on this, and I counted across here, and it actually says 560 turns on here, which says that there's like 112 there's like 112 loops that are visible, and then there's 5 layers. 5 times 112 gives us 560. Okay, and so that's what we've got on, and we've got some variations on this. The one that I'm actually going to use for the close-up has 540, but that's kind of what our wire coils look like. Okay, so yeah, so that one's 560, but the one we're going to use for the measurement is at 540. Let's see, we're going to have to find out how long this is. That's going to be taking those 540 loops and multiplying that, not by a diameter, it's by a circumference. Sorry about that. Let me get one more formula in here. So we'll say that the circumference is pi times the diameter, that's showing the diameter, and then the length is equal to 540 circumferences. Now, I'm going to have to do some averaging on that because remember, there's 5 layers and the circumference is going to get less and less. So what I'm going to need to do is, I need to get a ruler out. On the end here, you can see that there's a gray cylinder. That's what the wiring is wrapped onto. So that gray cylinder right there is going to give me an inner diameter, if I measure from side to side, from here to here, is going to give me the diameter of the piece of plastic that the wiring starts out at. So I can get an inner diameter, and then I get an outer diameter. I got to get out the calipers and do an inner and an outer diameter on this, so I'll do that. And then I'll average. I'll get an average diameter. That will give me an average circumference. And if we do an average circumference times 540, that will give me the full length of the wiring. So I will get to doing those measurements. Now the other thing that we've got to come up with is what's the diameter of the wiring itself? Again, let's go back and imagine what would this look like if I unwrap the whole thing. Well, a piece of wire is like a really, really, really long cylinder, right? It's got this little tiny circular cross-section, and then it goes on for hundreds of meters. So what we've got to do is find out what that circular cross-section looks like. That's the cross-sectional area. Now, a way to do that is I can get a ruler out and measure along here, and I'm going to be able to come up with a length from this side to the other, and then I can divide that by 112. Okay, so I can divide that through by 112 because they're closely spaced together. The insulation layer is really quite small. I'm going to ignore the insulation portion, and so I'm just going to divide this length up and determine what the diameter of each one is individually. So I'll get some of those numbers and I can report those to you guys. Because I'm your lab partner and I'm reliable because I'm staying caught up in the reading. You guys know all that storyline. Anyway, that's going to be enough information that we can come up and we can do a measurement of the resistivity for copper. So here we don't really have any accepted values to compare with in measuring the resistance, but certainly the resistivity of copper, that's something that there's an accepted value for. So we'll see. We'll see if our measurements give us something similar to what other people have measured for the resistivity of copper. All right, so let's take a look at the close-up setup for this lab. So we have the setups for circuit A and circuit B. So what we've got here is I've got a battery, which is listed as 1.5, but I think this battery is not providing that voltage. We've got a switch here. I like these old switches. I don't know how far back they date, but they are pretty cool. So I got an old switch here, and then we've got the coil. Now that's the wire where we're trying to measure the resistance. And so what I've done is I've put an ammeter in series with that. Here is the ammeter. That's going to measure the current. And then I got a voltmeter here, and the voltmeter is connected across the coil and the ammeter right now. So it's the same as we saw on circuit A. And I did some measurements on that, and I double checked them. So I got voltages of 0.92 volts and a current of 0.458 amps, and that's giving me 2.01 ohms. Now, what we said was the voltage here is probably going to be over, it's reading above and beyond what we want to include. So we're going to move the contact for the voltmeter over closer into the coil. So this should give us a better voltage measurement, but we're going to have problems with the current now. In any case, what did happen was that the voltage did really drop quite a bit. The voltage I ended up with measuring here was 0.73, so it was a pretty significant drop. So we've probably got some resistance, not just in the ammeter, but also in the wires. And these aren't really super precision voltmeters and ammeters, so it's actually in some ways it's a good measure of kind of what we talked about. So the voltage did drop quite a bit, and then the current went up some. And so the current now went up to 0.514 is what I was measuring. But now it looks like it's below what it was before. So I'm also seeing some drift in these measuring devices. So the resistance I got for the second measurement, 1.42. That's kind of what we talked about before. We're going to get a higher value on the first one, lower value on the next. Problem is that they're so different. It's kind of in question whether either one is really especially reliable. All right, time to move on to that bridge circuit and see what happens. So here is the setup with the bridge circuit, and let's just see where we are here. We've got a battery set up. I got a switch here so I can turn the whole thing off. The battery, and then here is resistor 2 and resistor 3 that we talked about. And I've taken the battery and connected it to the ends. In fact, what I've done is I bypassed some of these connection plates here with the idea of I want to get as close to the resistor wire as I possibly can. So I've clipped that directly onto here. Now, I'm expecting these wires aren't going to give us a big contribution in terms of resistance, but I'm starting to worry a little bit about some of the individual connections. If they're loose, they may be providing a little bit of resistance here too. So what I've got is the bridge circuit. Let's see, here's resistor X. I'm sorry, resistor 1, and then here is resistor X. So it's the resistor wire coil again, and then I'm running this through a galvanometer, and what you can see is that when I make a connection with R2 and R3, this galvanometer is showing that we're not balanced yet. So I'm moving this back and forth, and I don't know if you can see this, but the scale zeroes out about right here. So it's zeroing out at about 46.1 centimeters is where I found that. Now that's with the resistor box set at 1. So I wrote those numbers down. And then I moved on to setting number, 2 ohms in the resistor box. And then I'm looking to see where it zeroes out. And as I increase the resistance here, I'm seeing that it zeroes out, I would expect, farther along here. And now I'm zeroing out at 61.2 was the number I measured. When I moved this to 3 ohms, it zeroed out here at 69.8. So what I'm doing is I'm adjusting in the resistance box. I've gone from 1 ohm to 2 ohms to 3 ohms to 4 ohms. Now as the resistance increases here, then on this R2, R3 wire, the balance point is going to shift farther to the right. Okay, and so what I've done is I've done a series of those 4 measurements, and the resistances are coming out pretty close. I'm getting resistances of 1.17, 1.27, 1.30, 1.31. So that first measurement is a little off from the others, but the last 3 are pretty similar. Now my concern at this point is that circuit A and circuit B don't really match up very well with what I'm finding on the bridge circuit. So I'm going to go back and look at circuit A and circuit B again. I'm a little concerned about the voltmeter and the ammeters there, that they are not accurately calibrated. If I've got voltmeters and ammeters that are off, that's going to cause a problem for us. But the bridge method seems to show some real consistency here, so that's encouraging. All right, so what I've done now is it's the same setup that we saw. It's the bridge circuit, but what I've done is I've taken out the sample resistor that we were measuring before. So I've taken this out and I've replaced it with a voltmeter. Now the voltmeter is no longer being used as a voltmeter, it's just a resistor. So I'm finding out how much resistance this voltmeter has. Now I've got it at the lowest voltage setting. There's a range of different settings. There's a 3 volts, 15 volts, 300 volts. The lowest resistance should be for this 3 volt setting. So I went through and I started out by setting the resistor box at thousands of volts. Thousands of ohms, because I'm expecting, even at this low setting, the voltmeter will have a lot of resistance. So I did start out with 1,000, 2,000, 3,000, 4,000. I did some measurements at each of those settings for the resistor box. And the same thing as before. So I had this, right now I've got it set at 1,000. And the measurement I had there was at, let's see what we got. Oh, and I got to turn everything back on. I had turned it off to give the battery a bit of a break. And what I was seeing was that I'm getting this, you can see it's going on either side of 0 here. And right at 0, I was coming in at 25.2 centimeters. Now I'm noticing when I go back and I remeasure, I'm not coming in at quite the same value. So there is a little bit of variance here that we're ending up with. But in any case, there is consistency with the bridge setup. I'm feeling more confident using this circuit now that I've measured 2 different devices. Now, unfortunately, this resistor box only goes down to individual ohms. This can only be set as low as 1 ohm. And to measure the ammeter, my guess is that the ammeter will have lower resistance than 1 ohm. So I'm going to have to go pull out some other resistor boxes that go even lower. I guess I could try it with 1 amp. But let me do that. Let me switch out. I'm going to switch out the voltmeter. And I'm going to bring in the ammeter. So here goes the voltmeter. I'm going to turn the circuit off. Give the battery a bit of a break. Take out the voltmeter. Now for the ammeter, I think I'm going to set it at the highest reading. I'm guessing that that's where the resistance will be the highest. That's going to be the easiest measurement to make. I could try this. Let me see. I'm going to set it just on 1 ohm. So I've turned everything else has been zeroed out. I'm going to see if there's any chance of getting, I guess I got to turn it back on again. Let me see if there's any chance of getting now this is going to be pretty extreme. So I think, oh, maybe we can get this. So here is a reading at 1 ohm. And I'm reading this over at 80 It's 85.8. So let me write that down. Let me go find my pen again. So I've got this setting at 1 ohm. This is a little bit risky, but I'm going to try measurements of 1, 2, 3, and 4 ohms. Now it's gonna give me some pretty small readings off on this side. I'm getting some pretty small values for L2, but let's just see. So on this first reading, I am getting a 0 at, this time it's coming up at 80, well, it's coming right at 89.0. So I'm going to write that as 89.0 for L3 in centimeters. That would give me 11 centimeters for L2. Let me change this to 2 ohms. And I think what's going to happen here is I'm going to be shifted even farther. Yeah, the ammeter has such low resistance in it that 1 ohm here is going to be really, really, really high compared with the resistance here. And that's why I'm getting these readings that are so far near the end here. I think I will... Well, I was thinking I could try to get at least one more reading with this 2 amp setting. Okay, and there it is. But it's coming in at 98.3. So let me take I'm gonna go run some numbers here and see what we've got. So I did go back and I brought out one of our older resistor boxes. This takes us down to tenths. So with this resistor box, I was able to go down to 0.1 ohm, 0.2, 0.3, 0.4, and do a set of measurements for that. Now, the ammeter has such low resistance in it that the surrounding wires, the wires that it's attached to, are going to contribute, maybe more than the ammeter. So what we're measuring here is not just the ammeter itself, but also the surrounding wires. But what I'm seeing with this is that I'm getting maybe 1/10 of an ohm. So we're getting somewhere around 1/10 of an ohm for the ammeter, whereas with voltmeter, we were getting thousands of ohms. So kind of what we talked about at the beginning of all this is that the voltmeters are designed to have lots and lots of resistance, and the ammeters are designed to have very little resistance to them. All right, so that takes care of our bridge measurements. So I'm collecting all the data here. I'm putting together some data tables, and so I've got a number of measurements I need to go back and take with this bridge circuit. But what I did want to finish up with for today, with the presentation at least, is that we wanted to do these resistivity measurements, and we said that for that we were going to need to have some diameter measurements. So the wires are sitting on a plastic cylinder, that gray cylinder, and what I got for a diameter on this using the calipers was 4.8 centimeters. So I'm getting 4.8 centimeters for the inside of the wiring, and then the outside of the wiring I can access from here. And so as far as looking at the outside of the wiring, I want to make sure that the calipers reach to the center. They do. And the caliper readings on this came in right at 6 centimeters. So I've got inside surface at 4.8, outside at 6. The average value for the diameter 5.4. That gives me an average circumference of 17 centimeters, and multiplying by the 560 loops gives 9,500 centimeters or 95 meters. I think before I was suggesting that there might be like a kilometer of wire on this, and I think I exaggerated. It looks more like it's a little under 100 meters of wiring that's on here. So with that, we can go through, we can take the resistance measurements that we came up with, and we can include these dimensions now, and we can work back and get a value for the resistivity for copper. So, and that finishes everything up. So we've got our resistance measurements from circuit A, circuit B, from the bridge circuit, and now we've got all of the measurements we need to come in and get resistivity of copper.